Here's Bullseye Bob holding his rifle in a level position, horizontally. Suppose at the same time he pulls the trigger, he drops a bullet from his trigger hand. Question: which bullet reaches the ground first, the one fired or the one dropped? Let's drop in on my conceptual physics class where I do a demonstration that features this activity. There's a little device here that will shoot a projectile. Little spring here. I'm going to compress the spring. And when I do that, I can put a projectile here and watch this, gang. Little spring gun. Okay. Out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of downish. This one goes outish. Now I'm going to do them both at the same time. When I do them both at the same time, you guys got to figure out, hey, which one going to hit the ground first? The one that just dropped down or the one that goes out? A lot of people think, oh, the one that's fired out is going to be in the air for a longer time. You know why? The gravity going to start to pull it and say, oh, I didn't know you were moving, go ahead. And gravity not going to pull so hard. What do you guys think? Let's try it. I tell you what. If you hear this, all A's. All A's. For this course, all A's. Registrar say, Hewitt, my God, Hewitt, you got all A's in your class. I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you gotta do your homework, okay? Here we go, gang. Here we go. This next moment may be very important for a lot of you who have your, everything riding in your grade. All right, here we go. Here we go. Listen. What did you hear? How many heard this? Wishful thinking. We'll do it one more time in slow motion. All right? Now you can get a better look this time. Slow motion. Here we go. All right? Same time, gang? Yeah. Gravity doesn't take a holiday on an object just because it's moving. Back to our screencast. So we see that for a horizontally moving projectile, the time of fall is independent of what goes on horizontally. Horizontal and vertical components of motion don't affect each other. That makes sense. If you drop a pencil while standing in the aisle of a fast-moving airplane, the time taken to hit the floor isn't affected by the airplane's speed. Here we have Phil Physiker dropping a ball off the edge of a cliff. A tall cliff. Very tall. We show the positions of fall at 1-second intervals. In the first second of fall, it falls 5 meters. 1 second later, it's 20 meters below the cliff. In 3 seconds, it's fallen 45 meters. And in 4 seconds, the ball hits the ground. It has fallen 80 meters in 4 seconds. Let's pretend there's no gravity and Phil tosses the ball horizontally. We see it travels equal distances in equal times. We're assuming no air resistance. But there is gravity, and the ball falls beneath these points. How far beneath? The answer is, interestingly, just as far as if the ball fell from rest at each point. The positions of the ball would look like this. When we join these points, we find the path of the ball is a parabola. Yum! Let's look at some velocities. First, vertically. An object dropped from rest gains a velocity, v equals gt. G is the acceleration of fall, 10 meters per second square. So in 1 second, its velocity is 10 meters per second. At 2 seconds, 20 meters per second. At 3 seconds, 30 meters per second. At 4 seconds, it hits the ground with a velocity of 40 meters per second.
Oops, not enough space to show the full 40 meter per second vector, but I think you get the idea. Suppose Phil throws the ball at 20 meters per second. Then we have a 20 meter per second vector at each of the 4 positions along the green line. All these vectors are equal. 20 meters per second will be the horizontal component of motion along the parabola. We draw 20 meter per second vectors at each position. Next, we draw the vertical components. Again, not enough space for the 40 meter per second component. Then we construct parallelograms for each position. And with the parallelogram rule, we construct the resultant velocities at each position. Again, our lower vector runs off the page, but you get the idea, right? To calculate the magnitudes of these velocities, we use the Pythagorean theorem. V equals the square root of the sum of the components squared. We'll call the horizontal direction x and the vertical direction y. How much is the velocity at the 1 second position? It's the square root of 20 squared plus 10 squared. Your calculator will show you it's about 22 meters per second. How much at the 2 second position? Your calculator will show it's about 28 meters per second. And for the 3 second position? Your calculator will show it's about 36 meters per second. And how fast does the ball hit the ground? Your calculator shows it's very close to 45 meters per second. Once you understand the concepts, calculations can be fun. Yum? Let's take a look at what happens if the ball is tossed at an upward angle instead of horizontally. Watch what happens. Again, we first draw the ball's path as if there were no gravity, a straight line. And we show the positions of the ball for 4 1-second intervals. But there is gravity, so again, the ball falls beneath these positions. How far? Just as far as if dropped from rest at each point. This time our parabola has a different shape. How about if the ball is tossed at a downward angle? Note what happens. Pretty much the same physics. Is this yum or what? Now I want to leave you with a question. Phil Physiker stands on a raised platform and tosses a ball horizontally. The ball leaves his hand a vertical distance of 5 meters above ground level. His friends measure the ball landing 25 meters downrange. So my question is, what is Phil's pitching speed? How fast does the ball leave his hand? And the second question, how fast does the ball hit the ground? 2 questions. Think about them. Until next time, good energy.